transformation. So the name itself indicates that source will be transformed into another type. So we have two sources, voltage source and current sources. We can transform voltage source into current source and current source into voltage source. So this is possible with practical sources. Okay. So let us go. Practical sources can be transformed from one form to another, which makes the analysis simple, and also network can be reduced. That is the meaning of transformation. Practical sources can be transformed from one form to another. That is, you can convert practical voltage source into practical current source, or practical current source into practical voltage source. So based on our requirement, we can apply that transformation technique, and we can make the analysis simple, and we can reduce the final network into simplified form. Okay. Now this is the source transformation. This is a representation of ideal voltage source. How to identify it as a voltage source? Sorry, it is a practical voltage source. Practical voltage source are always having internal series resistance, and this is a load. And here, this dotted portion, it is practical current source with internal shunt resistance. SH means shunt. Here, SE means series resistance. Shunt means parallel. For parallel, uh, for current sources, always parallel resistance will be there. For voltage, always series resistance will be there. If both the circuits are correct, if this both the circuits are similar, then I can transform this voltage source into current source. I can transform this current source back into this voltage source. Then we have to go for formulas. Okay, what are the formula? Transforming practical voltage source into practical current source. This is your practical voltage source Vs in series with internal resistance. I can convert this one to current source. Then what is the value of I is? Remember Ohm's law. Okay, remember Ohm's law. Ohm's law states that V is proportional to I, or V is equal to IR. You have to remember this. So what is I? I is equal to V by R. I is equal to V by R. The supply voltage, source voltage divided by series internal resistance. That is the value of I you have to write. And the value of R, which for always for current source, you have to connect resistance parallel. No? Whatever resistance RS is there, no, same resistance you have to connect here. Here 5 ohms means here also 5 ohms. So RS should be equal to RSC. That means whatever series resistance is there, same value of series resistance you have to connect as shunt resistance. RS should be same as RSC. How to transform practical current source into practical voltage source? This is a practical current source with internal resistance RS, IS, parallel with RS, R shunt, RSH. You can convert this into voltage source. So again, here you have to apply Ohm's law. We have I, we have R. So we can convert into voltage source. Just multiply I with R. I into RSH is voltage value, and same RSH you have to connect in series. Now, some of the important techniques you should know while reduce the network. If two voltages are connected in series we can add voltages. Please remember, in series we can add voltages. So it is possible. Plus minus, they are in series. So it is matching plus minus. So both will get added. So V is net voltage is equal to, instead of these two voltage source, I can reduce to simple single voltage whose value is equal to V1 plus V2. Similarly, two voltage sources with opposite plus minus, this is plus minus, but here it is minus plus. Then you have to see which one is more. Which one is more? Suppose this is 5 volts, this is 2 volts. This is 5 volts, this is 2 volts. Then you have to subtract this. 5 minus 2 is 3. So net voltage value will be plus here only you have to write. The which one is having highest value, no? Magnitude, more magnitude. That's polarity you have to retain, because V1 is greater than V2. So you have to retain plus here minus here, and you have to write difference V1 minus V2 because it is plus minus, here it is minus plus. And two voltage practical voltage sources are connected in series. Above these two are two ideal voltage sources because there is no series internal resistance. If they are connected, we can just add it. If there are two practical voltage sources connected in parallel, how to reduce? So two voltage sources you have to add. You'll get plus minus plus minus plus minus plus minus. So you'll get net voltage as V1 plus V2. And two resistance are in series. R1 and R2 are in series. We know that if two resistance are in series, net resistance is sum of two resistance R1 plus R2. Similarly, if the polarity is opposite, resistance value is still R1 plus R2 because in series resistance are added. No changes in the net resistance is equal to R1 plus R2. But voltage values, it is plus minus, this is minus plus. So we have to take difference. Suppose V2 is greater. Suppose V2 is greater, you have to write minus here plus here because V2 is greater, no? And you have to write V2 minus V1. For example, this one V1 is 2, V2 is 5. Okay, so you have to retain V2 direction, V2 polarity, and you have to write 5 minus 2 is 3 volts. Minus here plus here 3 volts. You have to write. Suppose V1 is greater, you have to retain V1 polarities. What happens if I connect two ideal voltage sources in parallel? If I connect two ideal voltage sources, actually in parallel voltage remains same. If you have two voltage sources of different value, for example 5 volts here, this is 10 volts. 5 volts and 10 volts, if I connect like this, it is illegal because in parallel voltage is same, it should be same. Only it is possible only when V1 and V2 are 5 volts only, then only we can connect it. Otherwise we cannot connect like this. But all the sources which are available now, they are practical voltage sources. So don't imagine that we can connect like this that in a lab because all the sources are practical only. Only for assumption we can assume that it's a ideal sources. So it is possible only when V1 and V2 is equal to same, then we can consider that two ideal voltage sources are connected in parallel. If two voltage sources are in parallel, definitely both should have equal value. Now very important concept, this one, in series voltage can be added, no? What happens if two practical voltage sources are connected in parallel? If two practical voltages in series, I can add the voltages. If two practical voltage sources are connected in parallel, so the only way you can reduce the network is you have to convert this between this and we have practical voltage source with V1 internal resistance R1, and between this node and this node we have V2 in series with R2. So we have to convert these two practical voltage sources into current sources between same two nodes. The value of I1 is value of I1. If I convert this current source into voltage source into current source, value is equal to Ohm's law. V is equal to IR, I is equal to V by R. So V by R, I1 is equal to V by R1, and I2 is equal to V2 by R2. The same R1 you have to connect here. Whatever R1 is there, no, same R1 you have to connect in parallel. Similarly, and while writing the direction of the current, please remember it is always from minus to plus. If I convert this one to current source, current direction you have to write minus to plus side. Minus to plus side. This also upwards the minus to plus. And two resistance you have to connect parallel because for current sources you have to write parallel resistance. Now between this and this full is entire one node. This full is entire one node because no other elements. Here also there is no other element. This full is one node. And two currents are flowing from this node to this node. Both are going towards the node. So I1 and I2 will be added. I1 and I2 will be added. And between this node and this node, R1 and R2 are in parallel. R1 and R2 are in parallel. So net equivalent resistance is 1 over R is equal to 1 over R1 plus 1 over R2. It is simplified as R1 R2 divided by R1 R2. Suppose three resistance are there, then we can write net resistance is equal to 1 over R1 plus 1 over R2 plus 1 over R3. So if I calculate this, R1 R2 divided by R1 plus R2 will get, okay. And after that, we have to you have to reduce these two practical voltage sources into a single voltage source. Again, here we have in parallel, we cannot add voltages. In parallel only we can add currents. So that's why we converted two practical voltage sources into two practical current sources. Then we added two currents going towards the node above and two resistance. Instead of that, we have written one single resistance. After that, once again convert this current source into voltage source. So value of I is equal to value of I is I1 plus I2. Value of R is R1 R2 divided by R1 plus R2. Again multiply this I value with this. So the this two practical voltage sources are converted into single voltage source where V is equal to, okay, I1 plus I2. I value is I1 plus I2, this value divided by into R value is R1 R2 divided by R1 plus R2. So that is a, and same value of this R, same value of this you have connected in series. So see here, two practical voltage sources we cannot add. Solution is you have to convert it into current source. Current source means V1 by R1. So you have to add those two currents, V1 by R1 plus V2 by R2 is a net current you have to add. Then you have to multiply with the equivalent resistance. Equivalent resistance is R1 parallel R2 will get equivalent resistance. Then V is equal to I into R, and same value of R you have to connect in series with the practical new net resultant voltage sources. For voltage sources always you have to connect it in series. Coming to the current sources. In the current sources, ideal current sources are connected in parallel. If two ideal current sources are connected in parallel, we can add. So this is a one node, this is a node, two currents are going upwards. So net current is I1 plus I2. If both the currents are going down, we can add again. Both are matching now. We can add, and net correction you have to write downwards only. If one is going up, one is going down. One current is going upwards, another is currenting downwards. You have to retain the direction of which one is having magnitude. Here we are considering I1 is greater. So you have to retain I1 direction upwards, and you have to write I1 minus I2. Next important, very, very important. If two practical current sources are connected in parallel, I told no, in parallel we can add currents. Okay, in parallel we can add current. So this is a one practical sources. This is a second practical sources. If two practical current sources connected in parallel, we can add the currents. No, so I1 plus I2 both are going upwards, upwards. So net current is this one. R1 and R2 are also again parallel. So net equivalent resistance is 1 over R1 plus 1 over R2, which is equal to R1 R2 divided by R1 plus R2. Suppose if two current sources are connected in parallel series, if two ideal current sources, remember ideal current sources are connected in parallel, in series current remains same. For example, this is 5 amps, this is 3 amps. In your circuit, in your any circuit, if they give two current sources with 5 amps and 3 amps, then it is illegal. It is not correct, because in series current remains same. If two ideal current sources are given in this, both should have the same value. Okay, I1 and I2 should be same. I1 and I2 should be same. Otherwise, the problem is wrong. In series current remains same. Okay, if two current sources are given in series, then both should have the same value. Next, very, very important. Many times this situation will come. Two practical current sources are connected in series. If two practical current sources are connected in series, how to reduce? I told now in parallel we can add current source. Then if two current sources are given in series, we can add voltages. In series, we can add voltages. Suppose if currents are given in series, solution is we can add voltage in series. So you have to convert between this node and this node. There is a voltage source. There is a current source. This is second current source. We can convert this one to voltage source. Again, we can convert this one to voltage source. So what is the value of I? I is given, R1 is given. Current source with the internal resistance R1 is given. So V is equal to IR. So V is equal to I1 into R1. So to multiply I value with I1 value with R1, you have to write voltage value. And which are the resistance is parallel, no? Same resistance you have to connect in series. For voltage source, you have to write series resistance. Value of resistance will not change. Same value of R1 you have to write here. Similarly, for second current source, multiply I2 with R2, we'll get another voltage value. And same value of R2 you have to connect in series. Now these two are in series. Voltage sources are in series. So we already learned how to add two voltage sources are in series. So this is form. We can add these two voltages if the polarity is matching, and net to resistance is series. In series, resistance should be added. So here, see the polarity. When you convert current source to voltage source, okay, arrow mark set plus should be there. Arrow mark set plus should be there. Arrow mark is upwards. So this plus should be here. This is very, very important. Plus is here, minus is here. Similarly, for this one, arrow mark set plus. Arrow mark set plus. Now this voltage value V1 and V2 both are plus minus. So net voltage is also we have to add it V1 plus V2. And resistors R1 and R2 are also in series in this path. So net resistance is equal to R1 plus R2. So this is how to add two practical current sources which are connected in series. And one more important point, some redundant elements are there. We have to check what are those. Any element in series with ideal current source is redundant. Any element in series with ideal current source is 10 amps is there here, 6 ohm. It is a redundant element. So we can just ignore this and we can neglect and you can just remove it and you have to write short circuit. Don't write open circuit. Open circuit means current becomes zero. You have to write short circuit, just remove it. Because in series current remains same. Whether it is 6 ohm or 10 ohm or 1 kilo ohm, 2 kilo ohm or 1 mega ohm, current remains same in series. So that's why irrespective of value of resistance here, since current source is given, always for a practical current source series shunt resistance should be there. But here shunt resistance is not given, series resistance is given, so that you can ignore or you can it becomes redundant. So this 6 ohms we can just remove from the circuit. So this is converted into this type because current remains same, whether it is 6 ohm, 60 ohm, 600, 6k, 1k, anything, current remains same. So 6 ohms is redundant. Any element in parallel with ideal voltage source. This is the ideal voltage source because practical voltage source means series resistance will be there. This is ideal voltage source. Any resistance connected parallel to that, this can be ignored or redundant. This is redundant. You can just remove it. Like in current source, we read short circuit, but for redundant resistance, don't write short circuit. If I write short here, short means what? 0 volts. 0 volts in parallel with 10 volts. It is not possible. Okay. So this should be open. If I remove open, voltage across these two points is still 10 volts. Voltage across these two points is still 10 volts with this open. So this one is correct. Now this is correct because this is ideal voltage source because this is not having any series resistance. But this one is practical voltage source. Practical voltage source of 10 volts in series with the internal resistance 5 ohms. It is directly connected across ideal voltage source of 10. Then we know that in parallel voltage remains same. It is equal to 10. So here we can ignore these two and we can remove it and you can write just 10 volts only. So these two becomes redundant because in parallel voltage should remain same. We know that there is a voltage source exists, ideal voltage source. So always between this and this ideal voltage value will be there. This two we can remove it from the circuit. Let us do some problems in the next class.